we are on lecture 27, and it may be a short one today. Yeah, a little early. Okay, so for review, this was lecture 2 of 5. So we looked at signal source gain voltage, okay, and also looked at some design guides for common emitter amplifiers, upper bound for common emitter gain, small signal limit, and some differences between the MOSFET and the BJT for transconductance, output resistance, and intrinsic voltage gain. And we also look at AC analysis when you have your current blockers and your current bypasses here and here. And then for oh, thanks, right. Sorry about that. Okay, and for 26, we did like a summary. We looked at the differences between the types of transistors, bipolar and the field effect transistors, and different parameters right here. And also look at power for the BJTs and the FETs right here for of the drain, power for the sources for both of those right there. Okay, so for this lecture, we're going to start chapter 14. So remember, this material is not going to be covered on the exam, but it's going to be covered in exam 3. Okay, so we're just going to start off with the amplifier classifications, 14.1. Okay, so for amplifier classification, so remember previously we had the input signal, it was only applied at the base or the gate right here for the BJT and the FETs, those type of transistors. And the output was taken at the collector or drain right here or right there. Okay, but the thing is that these transistors, they have 3 terminals, right? And that may be used for the input. So you have the BJTs, you have the base, emitter, collector right here. And for the FETs, you have the gate, source, and drain right here. Now, what is most useful for input for the BJTs, it's the base and emitter. And for the input for the FETs, the gate and source right here. And for output, the collector and emitter, right? And for the output for the FETs, the drain and source. Now, this 4 resistor network, that's going to be used still for determining the Q point. And these coupling capacitors that we're going to attach to here, those coupling and bypass capacitors, they're going to be used to change the signal injection and the extraction points, okay, and modify the AC characteristics. Okay. So for the BJTs, so recall the large signal transport model in the forward active region. We have the collector current, base current, and emitter current. And you can see that they're all functions of this base emitter voltage. This is a thermal voltage right here, in each one of them. It looks pretty much like diode, right? Now, the thing is that if you vary the if you vary that collector voltage, it has little effect on the currents, and the early voltage is not included because of that. Now, this base emitter voltage, it's in the exponential, and so it's a really good choice for input, and that's why it's going to be there. So this base emitter voltage has a really significant impact on these currents right here. And also, since the base emitter voltage, if be broken up into the voltage between the base, or the voltage at the base and the voltage at the emitter, each one of those can be your input. Okay, so you could choose either of those. And this input from the collector terminal, that's actually quite negligible compared to the base and emitter. Okay, so now for these large current changes in the collector and emitter, they create large voltages across the across the collector resistor and the emitter resistor. So we're talking about this one right here and here. Okay, so there is some significant current going through there, and those are really good for outputs. Okay, However, since the base current is attenuated by beta F, which is the voltage gain, and made smaller than this IC and IE currents as a consequence, the base terminal is not normally used for an output. Okay. So for the FETs, recall the N-channel MOSFET drain current in pinch-off is this form right here. Here's the transconductance. Here's the voltage between the gate and source. And this right here is a pinch-off voltage. So to significantly vary the drain current or the source current, you need to change the gate source voltage right here. So you can either change the voltage at the gate or the voltage at the source. Okay. So an input signal voltage can be injected into the gate or the source. So there's a good input choices. Now, since a variation of the gain voltage VD has only a minor effect on the terminal currents, then VD is not a very good signal input right there. But substantial changes between with the drain current or the drain or the current source through this RD and R6 right here and here, those make good output ports. Okay, and this current right here is 0, so that's not used for an output port. Okay, so with those things said, this is what we have with the BJT and the FETs. Okay, so so for effective amplification, you can have as input, your input could be injected into either the base right here, or emitter, or the gate and source terminals of the transistor. And it can be extracted from the collector, emitter, or drain source terminals. Okay, so I have the IOs here. So I's for input, O's for output. So the base and emitter, those are good for inputs. The collector and emitter, those are good for outputs. And for the FETs, the gate and the source, they're good for inputs. And the drain and the source, those are good for outputs. And so with all that said, you have 3 families of amplifiers. Okay, and the 3 families are the common emitter / common source. You have the common base / common gate, or the common collector / common drain. And I'll give you guys an example of what those look like right here. So here's one family, second family, and third family. So the common emitter, common source, right here, common emitter, common source. Here's the common collector, common drain, and the common base, and the common gate right here. And we'll go into detail on these things as well over this lecture and the other ones that follow. Okay, so let's look at the common emitter and common source amplifiers. Okay, so we saw this expressed like this, right? So what we'll do is we'll take this resistor R6 and we'll split it in 2. So here's RE and R4. Okay, so that's what this resistor is being broken up into. And this R4 is going to be put in parallel with this capacitor right here, which we know by now is a bypass capacitor, and it's really important for controlling things. And same here. So this R6 is going to be broken up into RS and R4. And that R4 is going to be coupled with this AC bypass right there. Okay, so now the reason that we don't bypass all of the R6, we're only bypassing part of it, and that's to gain a lot of flexibility in setting the voltage gain, the input resistance, and the output resistance of the amplifier, emitter, or the source. Okay, so that's where you have that extended control from. So that's why they do that. Now, for the EC circuit, the signal injected into the base and taken out of the collector of the BJT right here, the emitter is a common terminal between the input and output ports. Okay, so this right here, you can simplify it into this, and then you can see the commonality between the output and the input. They share a common reference, and that's because we're doing these AC equivalents, right? So these right here become short circuits. This is bypassed, so that's why we only have this RE left over, okay? And that up there, that DC, that becomes grounded, okay? So that's why this VB right here is really these in parallel, and R2 are those in parallel. Same thing happens over here. These right here become short circuits. This right here becomes bypassed. So that's why you only have RS right there. And for RG, it becomes R1 parallel with R2 because that becomes grounded, R1 and R2. And for this RL, you have this R3 in parallel with RO. Okay, so the network topologies of the AC equivalents are identical, as you can see here. They have different labels, but the topology is identical. Resistors RE and RS are the unbypassed portion of the original R6. That's what's left over, right? These RE, RS resistors, they provide added degree of freedom to the designer, allowing the gain to be traded for input resistance R in, output resistance R out, our input signal range IN. I mean the input signal range IN. And these types of circuits provide moderate to high values of voltage, current gain, input resistance, and output resistance. Okay. Now for these right here, the common collector and common drain topologies, for CC and CD circuits, the signal is injected into the base or gate, here or here, and extracted from the emitter or source, here and here. The collector C and drain D are bypassed to ground by capacitors C3, right here and there, and they represent the common terminals between the input and outputs. So here's the simplification going from this CC right here and CD from here to here. Again, these right here are short-circuited. That's why this one just goes straight to ground because of that right there. And this right here is shorted. So this voltage right here is the same voltage that's going to be across this R6. Okay, but the load's going to change, right? This is 100K, this is 13K, and now you have this load which is 11.5K. So those are parallel after that. And similar thing goes on over here. Okay, but again, the AC equivalents, they have, the AC equivalent circuits have identical structures in both cases. And last, in summary of the CC and CD amplifiers, so they typically provide a voltage gain of approximately 1, but they do have a high input resistance and a low output resistance. The input terminal, the input signals can be quite large without exceeding the small signal limits. They're often called emitter followers or source followers. And another thing that's kind of interesting is that they're like a single transistor equivalent of the op-amp voltage follower that we know about. Okay, so much smaller real estate space for these types of voltage followers. Okay, so any questions about this short lecture? Okay, great. Any questions about the practice exam that we went over on Saturday? No, Sunday. Not yet? Okay. All right, well, let me know. And also, if there's any thing you guys want me to yeah, send me email too. Or if you guys need to, special office hours, let me know.